Hello, good evening, and welcome to our final public lecture in our Spring 2021 webinar series. As Laura said, my name is Amy Merkel, and I'm a research scientist at LASP, and I'm also the current lead of our Office of Communications and Outreach. It is my great pleasure to introduce you to our speaker this evening, Dr. Bruce Jakosky. There's Bruce. Dr. Jakosky is a professor in the Department of Geological Sciences at the University of Colorado and the Associate Director of Science at the Laboratory for Atmospheric and Space Physics. Dr. Jakosky came to LASP in 1982 as a postdoc and worked under the former director of the lab, Dr. Charles Barth. This fall will mark a remarkable 39 years serving LASP, CU, in the national and international science communities. Dr. Jakosky's research interests are in the geology of planetary surfaces, the evolution of the Martian atmosphere and climate, the potential for life on Mars and elsewhere, and the philosophical and societal issues in astrobiology. He has participated in many spaceflight missions over the years, including Viking, Solar Mesospheric Explorer, Clementine, Mars Observer, Mars Global Surveyor, Mars Odyssey, and Mars Science Laboratory. He is currently the principal investigator of the MAVEN mission to Mars that's been in orbit since fall of 2014. He's published more than 300 papers in the refereed scientific literature and has authored or co-authored a number of books, including The Search for Life on Other Planets and Science, Society, and the Search for Life in the Universe. As evidenced here, Dr. Jakosky is a leading expert in all things Mars, and I am personally looking forward to tonight's presentation. Thank you, Dr. Jakosky, for joining us this evening. I'll now turn the presentation over to you.
Thank you, Amy, and also thank you, Laura. It's a real pleasure to be here. I'm sorry we couldn't be doing this in person. It would be a lot more fun to be able to see everybody's faces and to be able to have a more interactive discussion. I hope that you're seeing my charts. Amy, can you tell me if you're seeing them okay?
Yes, we see them. Looks good.
Great, thank you. I want to talk about one of the my favorite topics. As Amy suggested, that topic is Mars. And what I want to do tonight is tell you a little bit about what's going on in the Mars community, because we have sent a whole flotilla of spacecraft to Mars that arrived this year. And it's going to be an exciting place as data starts coming back. But I also want to look ahead beyond what we're doing this year and talk a little bit about where the program is headed over the next few years and really possibly the next few decades and beyond that. I was watching the names of people who were logging in as we were getting ready to start, and I see a few names of people I know. You guys are going to keep me honest. I can't lie and cheat and steal, not with you there at least. So I want to start with figuring out how to advance my charts and bringing up a pointer so I can use it. You should be seeing a little laser pointer-like thing there. I'll get to that. I want to start with the idea that everything Mars seems to be very visible in the public these days. If you want to get your name on the front page of the New York Times, all you have to do is say something publicly about life on Mars or going to Mars or water on Mars, the history of climate. And I picked just a few examples here to show you that. The upper left shows a musical group called 30 Seconds to Mars. This picture was taken when they were performing in Estonia in Eastern Europe. The upper right, I hope everybody will recognize that as a scene from the movie The Martian, which was a big hit and hopefully is an omen of successful missions to Mars to come. The lower left is Elon Musk's Starship launching. He's tried about, I think we're up to serial number 11 or 12, and he's on his way to the moon, and then he wants to go to Mars eventually. And then in the lower right, well, you'll recognize the picture of Mars in the background. And if you know what that other thing is, I don't need to tell you what it is. If you don't know, there's no way I can explain it. So I'm not even going to try. With Mars being so prevalent, I think it's important to start with a discussion of why. What is it about Mars that makes it interesting? We see here Earth and Mars side by side. My best attempt to get them to the same scale so you can see them as their relative sizes. Mars is about 1.5 times as far away from the sun as the Earth is. It has a thinner atmosphere than the Earth, about 0.5% as thick as the Earth's atmosphere. And that means because it's farther away, because it has a thin atmosphere, it's colder. Temperatures at the surface average about 50 degrees C below the freezing point of ice. So it's a relatively cold place. On a nice warm day like today, that hits especially close to home. On Earth, we do have temperatures that get down to Mars-like temperatures if you go to the South Pole during the winter, but that's about it. When we look at the surface today, we see a cold and dry planet. You can see here 2 different images of the surface, one from Viking, one from the Curiosity rover. And really, it looks like a desert scene. Either one of these could be Earth, except for the complete absence of plants. When you look at this, you see a lot of evidence of windblown material or erosion of material. You don't see much in the way of water-related features. Despite that, though, we know that there's been liquid water on Mars throughout time. On the oldest surfaces, we see these things that look like branching river tributary systems where channels coalesce into bigger channels as they move downstream, downhill. And these look for all the world like runoff of liquid water. This occurs only on the ancient surfaces, so something happened to change that. When we look in the middle history of Mars, we see these broad flood features. I'll draw your attention to the scale bar here. That's 100 kilometers. So this whole thing, 150, 200 kilometers across, was filled with water at one time. That's as much water as the Mississippi in flood stage. The source of the water appears to be the subsurface, but the water is there. It was liquid beneath the surface. It flowed out over the surface, and we don't really quite know where it went. I often get the question of why do I think that these features were formed by water and not by something else? That something else could be the wind or volcanic magma flowing over the surface, lava flowing over the surface, liquid carbon dioxide or sulfur dioxide. And I resort to what I think of as a pretty technical explanation for why we think it's water. And I'm going to try it. This is the most technical thing I'm going to say during the talk. But when you look at these features, now I'll go slowly here, they look like they were carved by water flowing over the surface. That's one of the downsides of giving a talk on Zoom. I can't tell if you're laughing or groaning or if I just lost half the audience. But these features clearly appear to have been carved by liquid water. We see impact craters. This is Gale Crater, where the Curiosity rover is roving. You can see the rim of the crater around here. And all the evidence points to this having been a lake. There having been a lake filling that crater at one time during the middle part of Martian history. So there's been a lot of water. At the Opportunity rover landing site, we see these features that were termed blueberries. Well, this is a stretched image. I would call them less red berries. But these are exactly like concretions on Earth, formed when water flows through rock and dissolves minerals from one place and deposits them in another. And they were exposed at the surface by erosion. And finally, we're able to map out minerals on the surface that require liquid water to have formed. Most of these minerals here, the locations of which are on a Mars map, global Mars map, indicate that there's been liquid water flowing over the surface. that actually raises the most fundamental question we have about Mars, with liquid water in particular having been important throughout the history of Mars. Could there ever have been life on Mars? When we look at Mars, we see all of the things that we think are necessary to be able to support life in a planetary environment. I've been focusing on liquid water, and I hope I've convinced you that liquid water has been there throughout Mars history, but also access to all of the elements out of which life is constructed: carbon, hydrogen, oxygen, nitrogen, and a source of energy that can drive metabolism. That source of energy may just be chemical reactions between water and rock. A lot of the Mars program these days is geared toward answering this question of, did Mars ever have life? If it did, could there be life today? And that brings us now to the 2021 campaign of spacecraft to Mars. The one that is getting the most press right now is the Perseverance Rover. And this is a set of images from the landing in mid-February. I thought this was a brilliant maneuver on the part of NASA to put cameras on the thing as it was landing. So looking up, you can see the parachute that opened to slow it down. You can see the heat shield as it dropped away from the bottom. From the rover, you could look up and see the sky crane that was lowering it down to the surface, and the rocket nozzles on the sky crane that provided the powered descent. And then from the sky crane looking down, you could see the rover. This is just an absolutely spectacular set of images. The goal of the Perseverance rover was to land at a place where there was evidence for water and see what it finds. This is one of the first images sent back by Perseverance. It doesn't look to me like there's a whole lot of evidence for water here. If I really stretch, maybe I could imagine that these rounded rocks had been carried in flowing water, and that broke off all the corners and made them rounded. But then I see rocks like this that look like they may have been shaped by the wind. However, when we take a step back from this, we can see where it landed. It landed in Jezero Impact Crater, which is one of these places that was a crater lake. The rim of the crater is here. You can see the scale bar there. So this is about 40 or 50 kilometers across. There's an inlet over on the left side here where water flowed in, an outlet over on the right where it flowed out. And we think that at one time this was filled with water. If that's the case, this is a good place to go to look for evidence for life. The next image is exactly corresponds to what's in the red box here. It's a close-up view. And what you see is this inlet here, and then a delta consisting of material that was deposited as the stream or river flowed into the lake and dropped its load of material onto the surface. This looks exactly like the type of delta that you would see on Earth, where you have water carrying sediment into a lake and depositing it as it slows down. This was the main target for Perseverance. The actual landing site is over here, and it's going to tootle its way up and sample a lot of these features. The different colors represent different compositions, and by looking at the different rocks, at the full variety of rocks that are present, we have a chance of determining if there's any evidence for life. The rover itself carries a lot of instruments designed both to characterize the surface and to look for evidence for life. So it has, for example, a radar instrument that will look at the subsurface beneath the rover, and that'll tell us whether what the structure of the subsurface is, whether there could be liquid water or ice beneath the surface. Of course, there's a mast with a camera on it, and this camera has a zoomable panoramic camera, so it can take high-res or low-res images. It also has what's called SuperCam, which is, as it says here, a laser micro image that can remotely determine composition of the rocks it's looking at. And of course, a weather station, because we're interested in the weather everywhere. But the key instruments are on the end of this articulated boom sticking out the front of it. It's got an ultraviolet spectrometer that can look for organic molecules in the rocks. And if they're present in any significant abundance, it can identify what they are. It has a high-res version, and it has an X-ray spectrometer to determine what the composition of the rocks is. With this combination of instruments, we have the ability to not only characterize the surface and the materials and the environment, but to detect any evidence for present or past life, if it might be there. But the real kicker, the real value of the Perseverance rover is it has a drill that is going to drill out samples of rock and collect samples of soil. By pulling these together and bringing them back to Earth, we can study them here on Earth and get a real sense of whether there could be life. This, to me, is what makes Perseverance the most exciting Mars mission we've done in decades. Once we have the samples, Perseverance isn't able to bring them back, but it will collect them and leave them to be brought back by a subsequent mission. That mission is going to go pick up the samples, put them into a MAV, a Mars Ascent Vehicle that will carry them into orbit. An orbiter will grab onto the sample container, bring it back to Earth, and drop it into the Utah desert. Of course, we drop it onto the Utah desert because if something happens, well, Utah's expendable. Once we get these samples back around, that was a joke. I hope everybody understands that. I have nothing against Utah. Once we get the samples back to Earth, we can study them in the laboratory where we have a lot more instruments, a lot more tools available to look at them and find out if there's any evidence for either present or past life on Mars. I'm sure everybody that is here is aware of the Perseverance rover carrying with it a little helicopter called Ingenuity that was designed to try to test out aerial operations. It's taken 4 or 5 flights now, and they've been successful. So we now have another tool at our disposal if we want to try to study Mars. Right now, there isn't much that this helicopter can do. It has a camera, and that's about it. But it has the ability to scout out future sites to be investigated by the rover, for example. I threw this picture in. I threw this picture in because it was taken during one of the flights from altitude, and it shows the Perseverance rover off in the distance, and then the close-up over there. I think this is one of the most spectacular images that I have ever seen from the Mars program or from the planetary science program. I think it is so cool to be able to see a spacecraft operating on another planet and to know that it's really there doing what we want to do. Now, Perseverance and Ingenuity represent only one of the 3 missions that have gone to Mars this year. The second one I want to talk about is the HOPE Emirates Mars mission. This was developed by a collaboration between the United Arab Emirates and our very own LASP here at Colorado. It's an orbiter designed to study the upper atmosphere. It went into orbit. It was actually the first of the 3 missions to go into orbit around Mars, or to arrive at Mars in early February. That was an artist's view of what it looked like in orbit. This is an actual view of the spacecraft prior to launch, after testing. That high gain antenna, the round thing in the middle, is about 5 feet across to give you a sense of scale. This actually fits into what we would call a small spacecraft rather than a large spacecraft. It's significantly smaller, less capable, but more focused than many other missions. The goal of EMM, as we call it, the Emirates Mars mission, is to understand the atmosphere from the bottom to the top. So from the very surface through the lower atmosphere where dust storms occur to the upper atmosphere where gases can be lost to space. By studying the combination of the lower atmosphere and the upper atmosphere together, we get to see the coupling between the two And that really tells us something of substance about how the atmosphere behaves right now. And we can extrapolate to learn how the atmosphere behaved early in history, and in particular, how much gas has been lost to space through time. That being one of the major processes we think was responsible for changing the Martian climate. We've sent spacecraft to look at Mars before. We've studied the lower atmosphere. We've studied the upper atmosphere. So why send another one? And the reason is we put this one into a very different orbit. It's a high altitude orbit that's not great for taking high-res images of the surface, but it's really good for understanding the whole planet all at once. This orbit, this picture is shown to scale. It shows the orbit relative to the size of the planet and to the orbits of the two moons of Mars. And you can see the orbits sizes of the other orbiters that are orbiting, and they're all located relatively close in. By being far out, we can see all places on the planet at all times of day over a period of a week or so. And that really lets us get what we would call a synoptic view that has not been available from any other spacecraft. That combination of all times of day, all places, really is a powerful one, and we're anticipating doing a lot with that. I have to show the first image of Mars taken by EMM after orbit insertion. Just a spectacular image. You can see the three Tharsis volcanoes, Olympus Mons over there, Valles Marineris stretching off into the distance over here. In addition, it's making infrared measurements of surface and atmospheric temperature. These really tell us about the lower atmosphere and what we would think of as the weather, the behavior of CO2, the behavior of water, dust, as the seasons evolve and as Mars goes around its orbit. I'm not going to interpret these today, but this is just an example of what we're going to get many times of day, every day going forward. And then we have ultraviolet images that show the upper atmosphere, and these show the gases that are escaping to space. These gases, hydrogen, oxygen, and carbon monoxide that are shown in this image, are all the breakup products from water and CO2. And by tracking them in the upper atmosphere and seeing how high they are, how much is there, how the abundance in the upper atmosphere relates to what's going on in the lower atmosphere, we're going to learn a lot about the escape of gas to space. The third mission is the Chinese Chianwen-1 mission. Chianwen means heavenly questions. And this looks like a really goofy image of the spacecraft until you realize that it was taken from a CubeSat that was ejected from the spacecraft while it was en route to Mars, and it took a photo of the main spacecraft. Again, I think this is really cool to see an image of a spacecraft in space. The Chinese orbiter, which went into orbit 2 days after EMM, carries with it a lander and a rover. This is an artist's rendition of it on the surface. It's going to land probably next month. The orbiter and lander have science goals that really are consistent with the goals of all of these others, to understand the nature of the surface, the atmosphere, the behavior at all scales, from the millimeter scale that you can see at the surface to the hundreds of kilometer and planet-wide scale that you see from orbit. And of course, an image taken of Mars by the Tianwen-1 spacecraft as it was approaching. So these are the spacecraft in orbit and operating at Mars today and on the surface. I think this next year is going to be an incredibly exciting year. Normally, it's very exciting and engaging when one spacecraft sends back data, but we have 1, 2, 3, 4, 5 spacecraft that just arrived at Mars when you count the orbiters, the landers, the rover, and the helicopter. And they're all going to be sending data back to us. I want to turn now to going ahead. What have we got to look forward to? The next thing to launch is going to be from the European Space Agency. It's what they call the Exomars Rover. It's an exobiology at Mars rover. It's going to launch next year, and it's designed to look for organics and life. Wait a minute, this isn't the right one. This one was looking for evidence for plant life on Earth. Oh, this is the right one. This is the Exomars rover. You'll see the similarity, though. They're clearly cousins of each other. What is special about this rover is that it's going to drill down for the first time below the surface. The intention is to get 2 meters below the surface. And at that depth, you're deep enough that you're protected from cosmic rays and solar energetic particles that can destroy organics. So it's going to drill down 2 meters, bring up soil from that depth, and analyze it to look for evidence of organics or possible life. In the late 20s, I already mentioned sample return. We'll be sending the spacecraft that will bring the samples back. That will be probably the most elaborate mission that we will have ever done in planetary science, consisting of at least 3 spacecraft to land, collect the samples, which is what Perseverance is doing, put the samples into orbit and bring them back here. But the excitement is when they get back and we can see what they hold. Beyond that, although this one may occur earlier, is a mission called the Mars Ice Mapper mission, what we call MIM. This one is going to look for ice in the near surface of the planet at middle and high latitudes. We've identified ice, but we don't know where it is. This one is going to use radar in order to look for where the ice is. And it's looking at it as a possible resource to be mined and used as water when we send humans to Mars. That's something that we can do in the coming decades. I'm not sure when it will take place, possibly in the 2030s, the first human mission to Mars. This is one example of what it might look like. This is Lockheed Martin's Mars Base Camp concept, where they would send 2 of their Orion spacecraft, which are sitting here, 2 service modules, extended service modules, propulsion, crew quarters to Mars, and be able to do science from that. When can we do this? I think the earliest at this point is going to be the mid-2030s. What I think of is we're going to do this mission 15 years from when we decide to make the commitment to do it. We're in 2021 now, so mid-2030s if we decide today we want to do it. It's very feasible. Now, finally, I want to look into the far future. Mars had a warmer, more clement climate at one time early in its history. Can we terraform Mars? Can we bring it back to life, if you will, put gas back into the atmosphere, warm it up, and have liquid water flowing over the surface again? The idea of terraforming, making it look like Mars, is that if we put greenhouse gases in the atmosphere, we can raise the pressure, we can raise the temperature of the planet, and that would allow people to work outside without spacesuits. If we raise the pressure and the temperature, it would allow us to have liquid water, which will let us grow crops. It's very simple to do. All we need to do is add a greenhouse gas. The best greenhouse gas that might be available is CO2, and that's if we want to use today's technology. We'd need to find enough CO2 to raise the pressure to about the atmospheric pressure we have here on Earth. It's 1 atmosphere, or about 1 bar. If we could find that much CO2, it would raise the pressure, it would raise the temperature through greenhouse warming. This concept has been put forward by people like Elon Musk. I have a quote here from him. He says, "You would need to live in a dome initially, but over time you could terraform Mars to look like Earth and eventually walk around outside without anything on." I presume he means without a spacesuit. I don't think he's talking about nudist colonies on Mars, but I'm not entirely sure. He calls it a fixer-upper of a planet. Is this possible? So the question is there enough CO2 available on Mars that we can put it back into the atmosphere and raise the pressure and temperature? That's exactly equivalent to asking, where did the CO2 from that early thick atmosphere go? Has it been lost to space, or is it still on the planet? We can do an inventory of all the CO2 to answer that question. There's ice in the polar caps shown here. There's CO2 ice in the polar caps. And Elon Musk's idea of nuking the poles to heat them up and put CO2 back in the atmosphere would be able to mobilize it. There just isn't a lot there. There's CO2 in the ground. It's globally distributed. When you have gas in the atmosphere in contact with dirt grains, some of the molecules will attach themselves onto the dirt grains. It's a process called adsorption. If we could heat up the dirt, it would drive it out. The problem is that you would have to heat up the dirt globally, and you wouldn't be able to drive it all out. And as soon as you stopped heating it up, it would go back in. There might be a fair amount of CO2 there, but getting it out is going to be extremely difficult. There are CO2 bearing minerals, what we call carbonates. And if you could heat those up, you could drive the CO2 out and put it into the atmosphere. This is a one-way flow. You heat it up, it releases the CO2, and it stays in the atmosphere. The problem is you would have to strip mine a large part of the planet in order to get at the CO2 and in order to get at enough CO2 to raise the pressure. There might be a fair amount buried deeply, but then you've got to strip mine it down to a depth of 5 or 10 kilometers. And that is pretty implausible. Finally, some of that gas can be lost to space. And I mention this not just because we see it happening, but because it may be the dominant mechanism for having lost CO2 in the first place. And once it's been lost to space, it's gone. You can't get it back. The final thing we could do would be to wait for ongoing volcanism to release new gas into the atmosphere. This is a very straightforward process. Volcanism is probably occurring today, and it releases gases from the deep interior. We only have to wait long enough to get enough CO2. That would take maybe 3 billion years. So not something that's going to happen in the near term. So the question, can Mars be terraformed? I'm going to change that. Can it be terraformed using today's technology? Because we want to do it, if we're thinking about terraforming Mars, we want to be able to do it now. We want to be able to find this CO2 and put it back into the atmosphere. And I think the answer is that based on what we talked about in the last chart, there's a fair amount of CO2 there, but the amount that is abundant is hard to mobilize and put into the atmosphere. And the amount that is easily mobilized and put into the atmosphere is not very abundant. So the bottom line is you can't do it. You can't terraform Mars using today's technology. Now, I don't want to completely dismiss terraforming because we might be able to do it with new technology. We can create designer molecules that would be very efficient greenhouse gases, and we could manufacture them on Mars. We think the ingredients are there. The carbon, chlorine, oxygen. We could make molecules that would be very efficient. However, that's going to require a manufacturing capability that we don't have. We haven't even set people to Mars in a first attempt at a human mission. And the idea of creating huge factories as big as anything on Earth is pretty far in the future. So I think today's technology, not going to happen. Plus, I want to take a step back. I think there's a danger in thinking that we can terraform Mars, make it more Earth-like. And the risk, as described in this Calvin and Hobbes cartoon, is that if we think of Mars as a backup planet where we can go if we muck up the climate here, we're not going to take care of the climate here on Earth. If we think that Earth can be abandoned in favor of Mars, we're going to treat it as a disposable planet. no matter how far away from the current environment Earth gets, it's always going to be easier to fix the Earth than to make Mars like the Earth. So I think if we're going to terraform anything, we should terraform the Earth and keep it with the livable climate and environment we have today. This is my last chart. It's a walk-off chart. And I just want to say, especially as we're looking ahead to human missions in our lifetime, Mars is an incredibly exciting place to explore. We're learning about the history of not just Mars, but of all planets in our solar system. And we're learning a lot that's going to help us understand planets around other stars. We're exploring for life that will tell us whether life on Earth is unique, not just in our solar system, but maybe in the galaxy or the universe. And that really addresses a profound question that is of tremendous interest. So as we go forward, think of the missions this year as the first set of missions in Humans to Mars, because these are exploring Mars to find out what's there today, and they're helping us set the stage for exploration into the future. And that is my last chart, and I will stop there, and I'll be glad to take any questions.
All right, thank you so much, Bruce. We are accepting questions in the Q&A. Feel free to type them in there. We have a few questions so far, so we'll start with those. And as I said, please feel free to type in questions as we go. So the first question came in, and I think it was referring to Perseverance because it came in when you were talking about that, but what depths are targeted in the subsurface study?
I presume that's with the radar, and Perseverance, it has what's called ground penetrating radar. It sends a radar beam down from the spacecraft into the subsurface, and it'll bounce off anything and come back up. I expect that that will go to several hundred meters depth.
Okay, so then the next question is Mars Ice Mapper a synthetic aperture radar? And is it sharing technology that would be demonstrated on developed from NISAR? Is that how you say that?
Yeah. I believe the answer is yes, but let me elaborate. The radar on the Mars Ice Mapper would be contributed by the Canadians, and it's a system they've flown before. Honestly, I'm not sure if it's the same one that has flown on NISAR or not, but they have, it's what we would call TRL-9. It's ready to build and fly whenever the commitment is made. That's going to be an exciting mission. It is a synthetic aperture radar, but it's also a single dish. So it does imaging as the spacecraft traverses along its orbit. I'll stop there.
Okay. Okay, so how about this question? Do we need to create a magnetic field to prevent Mars's atmosphere from escaping and achieve that 1 bar goal?
So the idea of an artificial magnetic field has been put forward actually by Jim Green, who is the chief scientist at NASA headquarters in Washington. He suggested that if you could put a big magnetic field upstream between Mars and the sun, it would create a magnetosphere that would shield Mars from the solar wind. There's nothing wrong with that idea, except that it would have to be a really powerful magnet, and that's probably beyond our capability. Oh, and by the way, there isn't enough gas left to protect from the solar wind. The sun and the solar wind have stripped away a lot of the atmosphere, but all that action took place early in Mars history when the sun was more intense in the ultraviolet and when the solar wind was faster and stronger than it is today. So the bulk of the atmosphere was lost between about 4 billion years ago and maybe 3.5, 3.6, 3.7 billion years ago, over that period of just a couple of 100 million years. Today, the atmosphere continues to be lost. It's still being removed, but at a rate of only a couple of kilograms per second. At that rate, it would take hundreds of millions of years to remove much gas. Gas is still being added by volcanism, but I'm not really willing to wait the billion years for volcanism to replenish the atmosphere. And I don't think it's being removed at a rate that is great enough to significantly deplete it over the next thousands of years, 100,000 years. So I don't put much stock in this idea of an upstream magnetosphere, a magnet. I think it's a cool idea, and there's nothing wrong with it other than it's not necessary.
Okay, so there's a few questions about sending humans to Mars. One is, and I'm just going to group them together and you can address them how you want, but one's, what's the long-term effect of reduced gravity on humans? And then one's on, can you address the dangers of human travel and the effects of radiation and other hazards? And why would we send humans to Mars?
Let me do the what first and then come back to the why, because those are fundamentally different questions. In terms of the what, there are 3 or 4 things that stand out to me as major risk items that we need to address so that we don't lose crews, so that people don't die when we send them to Mars. One is the long time of being away from the Earth. A round trip to Mars might take as much as 2 to 3 years. Once you start, you can't get in trouble and come right back to Earth. One of the advantages of low Earth orbit is if there's a problem, you can land. Even going to the moon, you're only 3 days away if there's a problem. If you start to Mars, you might be 2 years away, and there's a risk that if equipment fails, you might get in serious trouble. That's a solvable problem, but it's a serious one. The second one that was identified in the question is gravity, or the lack thereof while you're en route. When you're in space, the lack of gravity has significant effects on the human body. Fluids redistribute, the muscles get weak, they atrophy from lack of use. Right now, the astronauts on the International Space Station have to spend 2 hours a day exercising so that when they return to Earth, they don't collapse under the force of gravity. It's a solvable problem, but something that people have to pay serious attention to. You can't lock astronauts up in a capsule and have them just sit there for 6 months while you're going there or coming back. The third problem is the radiation, not just from solar energetic particles, but from galactic cosmic rays. These can damage the human body and can cause cancer. I'm told that on a round trip mission to Mars, the amount of radiation that you are likely to accumulate in your body is greater than what OSHA allows for lifetime accumulation of radiation. It's a significant issue. In addition, the radiation can break bonds. If it breaks the bonds in the molecules in your head, you may get there, but you'll be a bit of a blithering idiot when you arrive. The other issue that concerns me the most in terms of health is the effect of dust on the surface and in the atmosphere. The dust, if you breathe it in, may be hazardous. We don't know if it's small particles or big particles. We don't know if they're sharp shards like on the moon or have rounded edges. So we don't know what the health effects are. In addition, they have minerals that are what's called deliquescent. They can trap water out of the atmosphere and liquefy and dissolve in it as liquid. If you breathe this stuff in, you're putting it into your lungs. We don't know what the health impact of that would be. All of these are very serious issues, but they're solvable problems. Because of them, however, I don't think we're ready to build a spacecraft today and launch it to Mars, no matter what Elon Musk says. I think we need to resolve these questions figure out the technical solutions to these before we can send people. And I think that's going to take the better part of a decade if we focus on it starting now. In terms of the why, sending people to Mars, in my mind, is similar to other ways of exploring the world around us. We send spacecraft to the other planets in order to know what they're like. We use telescopes to look at stars and galaxies elsewhere to know what's out there. And what we're interested in is questions like, how do planets work? Because we live on a planet. We want to know what planets are like. And we want to know how many planets might be out there, especially planets that might be able to support life. Is there life out there? We're not going to know the answer by sitting here and pondering it or sitting back in our armchairs and pontificating. We're going to know by going there. By finding out whether there is life elsewhere, it tells us about our own life here on Earth. We learn how unique are we. What we're trying to do is understand the nature of humans and the nature of our existence here on Earth by finding out about the other environments and whether there could be life elsewhere. One of my students put it bluntly a number of years ago. She said that we're exploring the universe in order to understand ourselves here at home. And ultimately, I think that's what we're doing. We're learning about the human condition. We're learning about what I think of as the boundary conditions that surround our existence and control it. And we're learning about ourselves as individuals, as a society, and as a species, and as an ecosystem. I'll stop there on that question, Amy.
Okay, that was good. All right. There's a question that's in the chat and not in the Q&A, but I thought it kind of tied in. So not into sending people to Mars, but really the long-term goals. What other scientific questions still need to be answered, and what type of technology now needs to be sent, since we have so many that are arriving and some that are planned? That would be the next step, I guess, of exploring Mars.
So that question is specific to Mars?
Yeah.
Well, I think we're on a path. First, we've been sending spacecraft to study Mars. We've been going along a path described by the theme of follow the water. Try to understand the history of water, where water has been, because water is necessary for life. We've transitioned in some sense to follow the life. We're looking for evidence of life. We're looking for, did Mars ever have life? Did it early? Does it today? Did it and it has died out? And trying to see if there is life there, is it related to Earth life? Could it have been transferred to Mars from Earth? Could Earth life have been transferred here from Mars? We've been exploring in situ with orbiters, landers. We're now on a path to bring samples back because we think that's the only way we're going to be able to answer that question. The next step is going to be sending people. And with people on the surface, we can much more quickly, much more effectively begin to answer some of these questions. It's a lot easier when you're there than if you're trying to do it robotically. I heard this described with regard to the opportunity in Spirit rovers, that in a year on the surface, they did what a geologist there could do in an afternoon. They did spectacular things, but it's slow going, and you can only send, a package the size of this desk and not send very many instruments. In addition to the water and life and human aspects, there's a lot about Mars we don't understand. The nature of the climate today, how it varies from one year to another, how the weather varies, the geological variability over the surface. We've explored, think about it, with rovers that can do the best job of looking in detail at one place. We've explored with, well, I'll start with the 2 Viking landers, but those weren't the instruments we would fly today. Spirit and Opportunity, and Perseverance and Curiosity. That's not very many places, and we haven't seen even a small amount of the variability and the range of possible characteristics that will tell us how the planet evolved. We're learning a lot about tiny places, but we don't know a lot about how it fits into the global picture and how all the different places around the planet might behave. The technology that we need to develop in order to do this, we need a lot of landers. Right now, they're really expensive. We need low-cost landers that we can instrument and put down in a bunch of places. We need long-lived, low-cost orbiters that can do a lot of science at relatively low cost, so that we're not so focused on each and every mission and what it's going to bring back, but we can look at all of the missions and send a lot of them and get a lot more data.
Okay, so I have a few questions about, or you have a few questions about the river, water, and so I wanted to hit on those. So one is, when you see the riverbed going into Jacero, it is meandering. Does this say something different about the river being longer lived versus a straight channel from a single or a few flood events?
Well, this is another reason I wish we were in person, because I could ask for clarification.
Yeah.
Look at the inlet. It looks like there's a little bit of a meander, but I wouldn't call it a meandering stream. The delta deposits look like they have meanders, but those are typical of delta deposits that form when a stream flows into a lake. So my gut reaction is, it's not telling us about what you think of when you think of a meandering stream here on Earth. I think the fact that we see streams, we see delta deposits, tells us that there was long-lived water. We see a lake. We see the evidence for a lake inside that big impact crater. Again, long-lived water, more than a year, more than 100 or 1,000 years. That makes it an interesting place from the astrobiological perspective.
So then, to follow on with that, there's a question that says, that a lot of the rovers, landers are landing in these craters. And is that really a representation of the rest of the Mars surface?
Absolutely not. And that's why we need to send a lot more spacecraft. What it is it's a direct result of this idea of follow the water. We're trying to go where the water was, because A, that will tell us about the history of climate and the history of water, and B, that's where the life is going to be, if there ever was any. You wouldn't, if you landed on Earth, you wouldn't necessarily go to the driest desert. You'd go to a place where there was long-lived liquid water to look for evidence for life. And that's what we're doing with these spacecraft on Mars. It's absolutely not representative.
And then one more question on just channels, floods, craters. There's a question about liquid methane versus water, and are we sure it's water? Could it be methane?
Methane, probably not, because I don't think that would be liquid under any conditions we could imagine on Mars. But the things it could be, I mentioned them earlier. Under certain conditions, you can get liquid CO2. Carbon dioxide, or liquid sulfur dioxide. But those things are not, SO2 is not abundant enough to give us liquid. CO2, maybe, but you need a very thick atmosphere, thicker than we think could have been there in order to liquefy it. Water, we have evidence for water. We measure water vapor in the atmosphere. We see water ice in the polar caps. We see in particular minerals that require liquid water in order to form, and those could not form from liquid CO2 or liquid methane or SO2. So we know there's been liquid water. What we don't know is how much and what the climate was like to support it. So I think it's worth considering alternatives, but all the indications point to liquid water.
Okay, and then I'm just going to ask one more question, and then we'll be done for this evening. But and it's kind of going back to the magnetic field questions or your topic. So one is, would you mind briefly explaining how Mars' magnetic field got lost in the first place? And do you think that all habitable worlds require a magnetic field?
That is a really good question, and I'm going to talk around that and not have an answer. We think that Mars had a global magnetic field like the Earth's magnetic field, a very strong one early in its history, because we see evidence for remnant magnetization of the crust. That is, when the crust cooled off, it would have taken on an imprint of whatever magnetic field was present. And we see this in regions of the crust that are old, the oldest parts of the crust. We don't see it on the younger parts. So we think that Mars had a magnetic field early on and that it shut off. The magnetic field, as on Earth, would protect it from the incoming solar wind and has the ability to protect the atmosphere from being impinged on by the solar wind and protect it from being stripped away. So we think that while Mars had a magnetic field, the atmosphere was probably protected. And when it turned off, that allowed the turn on of stripping of the atmosphere. Why did it turn off? Let's go back to why the magnetic field on Earth exists. The center of the Earth, the core, is an inner core of solid iron and nickel mixed together and an outer core of molten. As it cools off and solidifies, it drives motions within that core. And when you move an electrically conducting medium, it generates a magnetic field. So early on Mars, we think that the presence of a magnetic field meant it had to have a convecting core that was made of an iron-like or otherwise electrically conducting material. As Mars cooled off and the core froze, the magnetic field would have shut off. The core froze on Mars more quickly than on Earth, ultimately because it's smaller. It's more complicated than that, but for now I'll just say it's smaller, so it froze more quickly. And that would have shut off the magnetic field just after around 4 billion years ago. I think that answers the question. Oh no, there was another part, and that is a magnetic field required for a thick atmosphere? Is a magnetic field required for life? That's a question that is at the heart of a lot of active research going on today. In particular, Dave Brain here at LASP is exploring that with a multi-million-dollar grant from NASA to bring people from all disciplines together to address it. In fact, Amy, as you were reading that question, I thought, gee, that sounds exactly like something Dave would have asked me, just to see what I answer. But I didn't see his name when we were starting out. So
I don't think it was from Dave, but it could have been an anonymous. It could have been Dave, but I didn't see him. But he actually gave a talk on this a couple months ago. So
he just wanted to mention that he gave that talk a couple of months ago.
Yeah. So, okay. So are you up for one more? Because I know you love to talk about terraforming.
Go for it.
There's a question of, is there a better planet to terraform?
You know, I always thought that the ideal would be not just Mars, but Venus. Venus has an atmosphere that is 100 times thicker than the Earth's atmosphere and is CO2. All we need to do is take all that CO2 from Venus and move it to Mars, and we get 2 terraformed planets out of it. No, there isn't, to my knowledge and understanding, there isn't another planet or satellite in our solar system whose environment we could change to be Earth-like. The best we can do is terraform the Earth and not muck it up any worse than we already have.
Okay, well, I think that's a good message to end with. Thank you very, very much for your time and an excellent presentation. We very much appreciate it.
Thank you, Amy, for the invitation. It's always a pleasure to talk to the LASP public talks because people are so interested in this stuff. Thank you.